This video is going to talk about how to create potential energy graphs using a variety of chemical reactions. So I want to go through step by step of how to go about doing it. So often you have a chemical reaction. In this case, your chemical reaction is in words. So the first thing you need to do is create a balanced chemical equation. So let's do that right now. If you remember your alkanes, you'll remember that anything that ends with ANE is an alkane, methane being the first one. We have CH4, and it tells me it reacts with oxygen. Now remember, oxygen is part of the diatomic atoms. Have no fear of ice-cold berries. So I know that when oxygen is by itself, I write O2. Then it tells me carbon dioxide. Carbon dioxide I know is CO2, and water, which is H2O. All right, so the first step is to actually balance the equation. I know that I have one carbon here, one carbon there. I have 4 hydrogens here, only 2 here. I place a 2 in front, and that works out that I now have 2 oxygens here. And in this case, it looks like I have 2 oxygens here, 2 oxygens here, a total of 4. I have to place a 2 in front. So now I have a balanced chemical reaction. Now, because we're working with energy, I notice that there's a delta H value. Remember, delta H is a value of enthalpy, which tells you if you have a negative symbol, that it is an exothermic reaction. If you have a positive symbol, then it becomes endothermic. So in this case, I look and I see that it has a negative symbol. I know it's exothermic. So I need to place the word energy into this equation. Exothermic means that it releases energy as a product, and so for that reason, I'm going to place the word energy in the products. Okay, so I've balanced my chemical reaction. I've placed the word energy in there in the products because of it being exothermic. The second part is to explain why it's exothermic. Well, exothermic is the type of reaction I would expect, and I know that because of this answer right here. So I can place that right underneath there. That negative number tells me that it's exothermic. Okay, and the last part is to draw an energy, potential chemical energy diagram. So in this case, we'll call it chemical potential energy diagram. I have low and I have high. And usually I'll start with my reaction being somewhere towards the center. Okay, so I'm going to create a platform for myself, and I'm going to draw my reactants as particles. Okay, so I have 1 CH4, I have 4 circles. This is going to be my C, and these will be my H's. Okay. And then I also have 2 sets of O2. And the reason I'm drawing 2 of those is because I have 2 of them. Okay? So those are my reactants. I always know that I have, in the next step, I have activation energy required. In order to get these all separated from themselves so that they can rearrange themselves, there needs to be some energy involved and inputted. Okay, so in this case, they're all separating themselves. I have 4 H's, I have 1 C, and I have 4 O's. Okay, so now comes the next part. The next part tells me that I have an exothermic reaction, and these are the products. If it's exothermic, that means it releases all of its energy, so that all that energy that was potential energy is no longer potential energy, but has left the system and gone into the surroundings. Again, it has left the system and gone into its surroundings, and so for that reason I have less potential energy than before, and I make sure that my platform is below the reactant platform. So you'll notice that it is at a lower level. It has low chemical potential energy, and I simply draw the particle model. So in this case it is CO2, just one of those, with two H2Os. All right, so that's essentially how to draw a particle model. You want to balance the chemical reaction. You want to write the word energy either in the reactant or the product side, depending on what type of reaction it is. And then you remember, always make sure that you give your reaction activation energy. All reactions, whether or not they're exothermic or endothermic, require an activation energy. And then depending on if it's exothermic or endothermic, you write the products. Exothermic means the energy has left from the system to the surroundings, so you're left with low potential energy. So let's take a look at one where you have instead, in this case, you'll notice that you have a positive value. So for number 2, where it asks, is it endothermic or exothermic, that positive value, you know that it is endothermic. This means that it takes in energy, and we know that because of that positive symbol. That helps us out. So let's go ahead and write down the equation. You have hydrogen. Remember, hydrogen is part of the have no fear of ice cold berries. Reacts with oxygen to produce water. Okay, again, oxygen, have no fear of ice cold berries. It's by itself. You need to make it diatomic. Let's balance it. It looks like I have two hydrogens here, but 2 oxygens here. I need to place a 2 here, which now makes 4 hydrogens. I place a 4 here. Now, next I need to include the word energy. Because it looks like it's taking in energy, energy has to not be a product, but it has to be a reactant. So I write the word energy plus H2, 2H2 plus O2 reacts to make H2O. So in this case, because it's endothermic, I make the energy be part of the reactants. So I again create a chemical potential energy graph. We have low, high. And in this case, I again put my platform somewhere between the middle and the low. And it looks like I have 2 hydrogens, but 2 sets of those because of that coefficient of 2. And I have 1 molecule of O2. Again, as always, you need to have an activation energy. So this is our activation energy. So in this case here, it's that activation energy. That energy is required to separate all of these hydrogens and oxygens. Every bond, to break that bond, you need to have energy for that to happen. And because this is endothermic, that means it takes in energy. It actually now has even a higher potential energy because it's taken that energy in. So the H2O in this case is not at low energy level, but at a high potential energy level. And that's because it has taken in that energy. So in this case, your platform is going to be relatively high. And so here's how you can tell. So whenever you have an endothermic reaction, this is how you would see the potential energy, chemical potential energy. Whenever you have an exothermic chemical reaction, you see that it drops down. That's the difference. Both of them still have that activation energy that they require.